Well, hey guys, this is Mr. A, and this is our last video for the final unit of Math 8. And what we're going to do on this video is we're going to discuss pages 7 and 8 of the notes, and we're going to talk about a technique we can use to count outcomes of multiple events that have lots of combinations. Okay, so a tree diagram is not going to be a feasible tool in that case, so we're going to talk about a different way to count. And then we're going to finish it up with some maybe a science connection where we look at some different probabilities based upon data real fast. Okay, so we're going to start here on page number 7 of the notes, and we're going to talk about an idea here called the multiplication counting principle, which is right here. Okay, and basically what this allows us to do is allows us to multiply outcomes of single events together. All right, and we don't have to list them by the tree diagram or anything like that. We can just count them by multiplying, and then we can get a total amount of outcomes for a given scenario. All right, so I'm actually going to demonstrate this by actually going right into the examples, and we're going to do examples 1 and 2 together. Okay, so 1 and 2 together, and then I'm going to leave you 3 and 4 to do. I'll give you a hint on 3, okay, that you can do that one, and then we'll do leave you to do 4 on your own. Okay, so we're going to start here with example 1. I'm going to read it to you, and then we're going to go over it together. So you and a friend take turns guessing a secret number. The number is 4 digits, and the numbers may repeat. Okay, so that's actually important that they can repeat, because sometimes they can, sometimes they can't. So we need to know how that affects our count. All right, and the question becomes, how many combinations of numbers are possible? Well, if you have a 4-digit number, let's just go ahead and map this out. So we have 4 blanks right here, okay, for our number. And each of those blanks can be a digit 0 through 9, okay? So if I count 0 through 9, okay, as a possibility, then that means I can do 0, 1, 2, 3, 4, 5, 6, 7, and 8. Whoops, that's a really bad 8. Let me fix that. 8 and 9, okay? Then if I count all those options up, I count up all those numbers, I get 10 possible digits for each spot in the secret number, okay? So for example, this one can be 0 through 9, then this one can be 0 through 9, then this one can be 0 through 9, and then this one can be 0 through 9, okay? So, for the first digit, I can have 10 possible combinations, okay? 10 possible numbers to select from, 0 through 9, okay? And we count 0 and 9 here also as possibilities. That's why I listed them all out in my list, all right? And then for the second number, I can, again, because they can repeat, okay, I can select from 10 numbers. The same thing happens for the third, the same thing happens for the fourth, all right? And then the multiplication counting principle says I can multiply the possible outcomes of individual events together. So 10 times 10 times 10 times 10 becomes 10 to the 4th power, and that simplifies to 10,000. Okay? So basically what we just did was we solved the passcode problem on an iPhone, where you have a 4-digit passcode. There are 10,000 combinations of 4-digit passcodes. So if you have a phone or an iPad that has a 4-digit passcode on it, then there are 10,000 different ways you can generate that passcode. All right, so it's the same idea. Now we're going to look at problem number 2. Okay, together. And this one involves some letters and some numbers. Okay, it's still 4 digits or four items. So we're going to make 4 blanks. Okay, like we did before in problem number 1. I'll read it to you. A computer's password contains 2 uppercase letters followed by 2 numbers. How many password combinations are possible if both the letters and the numbers, again, can repeat? Okay, it can repeat. So I'm going to talk about, first of all, the numbers here, because I'm going to talk about the difference between them repeating versus them not repeating, and that'll give you a little bit of a hint for problem number 3, okay, down here that you're going to work on your own, okay, and check your answer on Canvas with the answer key. All right, so let's focus right now on these two spots right here, spots 3 and 4 for the numbers, okay? Again, we have all the options 0 through 9, okay? So this is just a replication of problem number 1 for those two spots because they can repeat. So this is going to be a 10 in spot number 3 and a 10 in spot number 4, okay, for the numbers. Now, if you read problem number 3, it says refer to the situation in problem 1, except the numbers now cannot repeat. Okay? So if they cannot repeat, that means you're going to have one fewer option for each new digit in the number. Okay? So just to model this for problem number 2, I would have 10 for the first number, but then I could only have 9 for the second number. Okay? So this is good information for problem number 3. Okay, so I'm going to erase that so we don't get confused, but that's a little hint for problem 3 because you're going to work problem 3 and 4 on your own. Going back up to problem 2, now let's talk about the letters, okay? And they are uppercase letters, so they are going to have 26 possibilities for the first letter because there are 26 letters in the alphabet. And then, since it can repeat, okay, 26 letters for the second option. Okay, if I multiply all those numbers together, we'll put this over here so we have a list of our options here. So 0 through 9 for the numbers, 26 letters. Multiply all those together, 26 times 26 times 10 times 10. You go to your calculator to do that. I would have 67,600 different combinations of a password. Okay, so much more. A lot more combinations than just doing all numbers all across the way. Okay, so you got lots more combinations this time. Now, there was a follow-up question with problem number 2. It says, what is the probability of selecting the correct password? Well, out of all those combinations, only one of them is the correct password. So there is a 1 in 67,600 chance of selecting the correct password. So we'll go ahead and box that in. Perfect. Excellent. All right. So those are the two answers for problem number 2. Okay. So problem 3 and problem 4 work very similar to that. And that's going to be how you use the counting principle to find combinations of possibilities, possible outcomes for large quantity situations. Okay. All right, let's go to the last page, and we're just going to really quickly brush up on this. I'm actually going to do all the examples on this page, but it's going to be very, very quick, okay, because there's not going to be much to talk about here. All the probabilities we've been discussing so far are called theoretical probabilities, okay, so I'm on paragraph number 2. And theoretical probabilities are probabilities based on theory. What should happen? For example, if I toss a coin, I have a 1 in 2 chance of tossing heads versus a 1 in 2 chance in tossing tails. Okay? So theoretically, if I toss the coin 10 times, then I should get heads 5 times and tails 5 times. All right? That's based on theory. Okay? But let's say I actually toss the coin 10 times and I get 2 heads and 8 tails. Well, then those probabilities then are based upon my experiment or my data, okay? So an experimental probability is based on what actually happened in my experiment. So in this case, I tossed the coin 10 times. I had 2 heads and 8 tails. So the probability, the experimental probability then would be 1/5, 2 out of 10, okay, of tossing heads, and 4/5 or 8 out of 10 for tossing tails, okay? So experimental probabilities are based on data, okay, or your experiment, and theoretical probabilities are based on fact or what is supposed to happen, okay? And just so you know, theoretical probabilities are what we've been calculating all throughout this topic, okay? So from the very beginning, we've been doing theoretical probabilities, okay? Going on example 8 here, it says the 6-sided number cube was rolled 30 times, okay? And we want to know for problem 1 the experimental probability of rolling a 4. So I'm going to highlight the 4 row and note that in 30 rolls, we rolled a 4 6 times. Okay? So the experimental probability of rolling a 4 would be 6, because we rolled it 6 times, out of 30 total rolls. Okay? I'm going to reduce this fraction by 6, and that becomes 1/5. Okay? Now, we should know by now, problem number 2, the theoretical probability of rolling a 4, that's 1 in 6. Okay, because there's only 1 4 on the die, right? There's only 1 4 on the number cube, or the die. So 1 4 out of 6 sides. 1/6 is my final theoretical probability. So now you can compare the experimental probability with the theoretical probability. Okay, you can see the difference there now. Okay? Now, we can also use our experimental probability, okay, to make predictions for larger experiments. So that's what's happening here in problem number 3. If we roll the die, or the number cube, 900 times, it says based on these results, so the results are up here in the table, okay, how many times would we be expected to roll a 4? So basically, I'm going to take my experimental probability, which is 1/5, okay, I rolled a 4 1/5 of the time. All right, so I'm going to take my total number of rolls, which is 900, and figure out what 1/5 of them equals. Okay, because a fifth of them should be a 4. So I'm going to multiply these across. I get 900 over 5, and divide by 5, and I would get 180 times that I should have rolled a 4. Okay, in my experiment, if I extended it to 900 rolls. All right, so that is the difference between experimental probabilities and theoretical probabilities. All right, just a little bit of an extension here. You're not going to have any assignments over experimental versus theoretical. That's not necessary right now. So just a little extension so you can kind of connect this to your science classes when maybe you did some genetics work or that kind of thing. But in a nutshell, guys, this is all the notes I have on probability and counting techniques. So we are officially now done with Math 8 for the topic, the unit, the semester, and the entire year. So congratulations on that. I just want to remind you that if you have any questions or concerns, you can email me at any time or send me a request to hang out on a Hangout chat, and we'll get all your questions and concerns cleared away before you take the assessment. All right. If I don't hear from you again, best of luck to you next year as you take Algebra 1 at the high school. And I wish you a great summertime here and a great start to your high school career next year. And if you have any questions or concerns, you know how to get me. So take care. Hope to see you soon, and enjoy